Welcome back to the lab. Today we're going to assemble the next UPS board, serial number 2. You feeling lucky? I sure am. While we're at it, let's implement the fixes that we just identified in our last video to make us just that little bit more lucky. Most of all, let's just have a little chat. Let's talk about how the project's going, and if you want a more detailed look at assembling one of these boards, check out the live stream archive or the official assembly video. If you still can't find what you're looking for, let us know. We've got 3 more of these things to build, so I'm sure we can find a way to work it in. Alright, so we have a lot to get done in this video, so we better get to it. Winding the transformer alone took us almost 4 hours. Why? Well, we wanted to make some modifications to the transformer bobbin. We wanted to optimize how we bundled the strands of the enamel copper wire together. One thing led to another, but we sure did improve solderability. So yeah, side note, blowtorch burns enamel real well. Making these improvements, followed by actually winding everything onto another transformer bobbin, took quite a while. Thankfully, I think we have a good process down for our next transformer, so they won't take so long. With the new transformer ready to rock and roll, let's start with the circuit modifications. We need to replace a few components for the gate drive in our push-pull converter. This is a bit of a review, but this rework prevents us from applying 40 volts to the gates of the components, which is important because if we did that, they would break. This rework is a trade-off between simplicity and efficiency. And if we find out that we need better efficiency performance, we'll have to use a dedicated voltage source to source the gate drivers. I think that we might be able to leverage the fan supply voltage if worst comes to worst, but that rework requires cut traces and jumper wires, so let's avoid that until we can't. Just a little too bodgy for my taste. I really don't like adding point-to-point wires. Our second rework will be adding a snubber to the push-pull converter, adding a 0.1 microfarad cap and a 10 ohm resistor. It's not a perfect snubber, but it's the best we can make with the parts on hand. The reason why I want to add this is because the overvoltage stress was our number 2 suspect for why these transistors may have failed short, but we won't know until it's too late. Hopefully this snubber will be good enough to keep our transistors from becoming damaged until we can collect some data and design a snubber appropriate to squash these transients. We don't have any special reworks to do in this case for the inverter failure. That's just something that we need to keep in mind, keep our eye on. And we added a bring up test to our procedures to make sure that that really does get done. We're not going to do that in this video, but it's tracked and it'll happen, okay? You can keep me honest if you want. The hot swap controller. What are we going to do? Buy hot swap controller? We just can't use it right now since the thing trips out all the time and it's going to interrupt our other testing. Let's focus our debug on the downstream circuits, the ones that we can really hone in on, and circle back to the hot swap controller once the inverter and push-pull converter get sorted. It's possible that once we're using a properly rated DC power supply, the issue might just go away. So at this point, everything on the board is the same as our previous one except for the reworks. Those 3 issues just turned into a handful of small changes. So, alright then, roll the time lapse. Let's get this thing put together while we have a little water cooler talk about how this project's going, what our thoughts are. Our conversation can get pretty calculated sometimes, so let's take this opportunity to loosen up a bit and just have a little chat about the project while we finish up this board. I have built quite a few things. I've designed more circuits than I can count. Many of these circuits solve very different problems. Some of these circuits involved microcontrollers in one form or another. A few of these systems were pure analog solutions. And, well, I don't just enjoy writing software due to the nature of it. I've used software as a tool to get something done. There are parts of software development that I like, but, oh boy, creating a push-pull converter, designing a custom transformer, creating this inverter stage, there are a few pretty awesome parts of this UPS project that get me so excited. It's like an analoger's dream. High power conversion, or at least higher power than usual. If there's one thing that I've learned through my experience with designing electronics and just building things in general, building something is real hard. Like, think about that for a moment. I single-handedly organized over 1,000 components to create something capable of serving a larger purpose. Wow! When architecting something like this, it's very difficult to do without making some little mistakes, just missing a couple small details. I mean, there's so many individual components to think about. How could I possibly be thinking about all 1,000 parts all at the same time? You just can't. Large companies, huge organizations with hundreds or thousands of employees still struggle with managing the complexity of needing to think about the high-level picture of a product while developing such low-level details. It's not an easy problem to solve. And on top of this difficult problem, there's always schedule pressure to get something out the door. There are always cost limits. There are always these extra factors that makes a person just make some compromises in their work, to make some concessions while designing something. Sure, any electrical engineer can probably design the UPS that we made here today. Give them enough time and money, it'll get done. However, if we ask those 100 engineers to solve this exact same problem, to design this UPS, I'm betting that we would get 100 different designs. No two would be exactly alike. Some designs would properly consider isolation. Many of the designs would likely make a sine wave. A few of these 100 designs would probably make a sine wave around 60 Hz and around 120 volts RMS. Some would be digital, some would be pure analog, but you know what? I'm sure that 100% sure that every single one of those designs would have a problem. 100 out of 100 UPSs would have some unintended feature, some bug, some element of its performance that isn't ideal. Whenever anybody tries to design an electronic device with hundreds or thousands of components involved, there is just bound to be some little issues. Finding these little glitches is exactly why the prototype phase exists. There's a level of careful analysis and design that is simply required when designing an electronic device. The design phase solves the obvious problems. That's what it's meant for. It ensures that the circuit is architected in a reasonable way. The analysis done here should prevent catastrophic failures like components being thermally overloaded. The design phase should catch things like power sequencing requirements, input voltage ratings, determining component values, those sorts of things. This design gets your components organized in a sort of way so that fundamentally they're just kind of put together right for what you're trying to do. Ideally, for a prototype, these circuits should be organized in a way that allows for a reasonable amount of reconfiguration. The more flexibility that we can bake into a circuit, the more hooks that will provide me when it's time to start debugging. All this to say, yes, we built a UPS and it wasn't perfect. I've built a lot of things that weren't perfect, especially when it was the first time I tried to make it. We found a few problems with our work when we were building our prototype inverter. You know what? I think that's okay. Then we took that prototype inverter, implemented the fixes from what we learned, and then we built that into a UPS. And you know what? That UPS wasn't perfect either. And I think that's okay. Why? Because we're learning. And not only are we learning, we're learning lessons from my favorite teacher, physics. We're applying critical thinking and problem-solving skills to find the true root cause of issues that we've never faced before. We're honing our debugging skills. Our circuit design skills are being exercised. We're exploring the minutiae of switch mode power supply topologies. And we're building something that doesn't really exist in the world the way that I want it to. Sure, there are many UPSs available on the market. Sure, there are pure sine wave UPSs available on the market. Do they cost more than we like? Yeah, they do. Do they have big enough batteries or long enough runtime for what I want? No, they just don't. And now, I know our design is not perfect. I know there's still a lot of work to do to go from where we are to where we want to be, and there's that gap between that. There's just that gap that exists. But I think we're doing pretty darn good. After all, in our first pass, sure, the board's broken, but in our first pass, we were able to build something that's capable of making 250 volts DC and was ultimately used to make a sine wave with the correct amplitude. But boiling this all down, do I think our design is perfect? No, absolutely not. Do I think the UPS would have been better if we had more time to invest? Yeah, I really do. Do I think this UPS would have been perfect if I had a team of 10 engineers designing it and we took as long as we wanted? No, it still wouldn't be perfect. And most importantly, am I happy with the UPS I was able to design with the time and resources at my disposal? Yes. Knowing the full constraints of this design, knowing exactly how much time and energy I had to invest into this UPS, I think that I did a good job. That said, good isn't great, good isn't perfect, so let's talk about where I think I could have done better. Where do I see room for improvement in this whole thing? Well, if I'm being totally honest, our design was a bit rushed. I tend to have a lot of priorities, and in these priorities, there are some parts of my life that, quite frankly, call dibs on my time. And I'm pretty limited when it comes down to what I have left for messing around in the shop and having some fun by building something. When it comes time to make something, like when I really want to design something big, like this UPS, it can take a really long calendar time, even if the quantity of project hours is pretty small. What I'm trying to say is that time was my biggest constraint in this design process. Time was the thing that we had the least of. Now, I wish that I could have slowed down for a month or 2 or 3, carved out more time for digging into the design, analyzing every aspect of it. And if we would have done that, I think that it would have been better. We would have found a lot of the issues we're running into right now, but then we would have gotten our boards in April instead of February. We wouldn't even know if they work yet or not. Now, I remember exactly why and when I shipped this design. I distinctly remember my rationale. We shipped this design not because we thought it was perfect, not because we thought we'd caught every glitch, but because I had reached my limit. It had been so many calendar weeks since I started designing this UPS, I was starting to forget the decisions that were made at the beginning of the project when I was where I was. We're not talking about just weeks here, we're talking about months. And I realized that the problem was only getting worse. I was forgetting things about the design faster than I was relearning them. And ultimately, I just didn't feel like I could justify the time and effort involved in reverse engineering my own work for a project that was supposed to be fun. Besides, I was around 80% confident that past EEforEveryone made some good, rational design decisions, and come on, how could you not trust this face? We weren't making big design changes either. Like when we were finding mistakes, we were finding errors, but we're talking like resistor values, component footprint mismatches, little optimization things, like not design changes. I felt like I was just running out of time. The design was pretty good, and I was prepared to take on the risk of shipping a design before it was completely polished, at risk of hitting a couple extra roadblocks. Most of all, I was, and still am, so excited to get this UPS working. I'm so excited for whenever we get this design on the bench and push its limits. I don't mind a little bit of troubleshooting. I don't mind a couple of reworks. Hitting these stumbling blocks is how I really learn. And these memories, these pain points where I'm spending hours slaving over the board and putting reworks on to mitigate these issues is how I will lean into these problems and learn in a way that I will never forget. As long as we can get 700 watts of pure sine wave goodness out of this UPS without spinning a new PCB, I'll be a pretty happy camper. That was a lot of chatter, but what am I really trying to say? I think that some simple mistakes really slipped through the cracks while we were designing this board. I really think that we should have caught the fact that our push-pull converter transistors were being driven with 40 volts but were rated for 20. The thought of giving this controller a constant voltage source crossed my mind more than twice while making this design. I should have listened to my gut and made that change. This was just absolutely and undoubtedly a boneheaded, preventable mistake. That was something that anybody who understands numbers could have figured out. You don't need to be an electrical engineer to understand that 40 is greater than 20, and if there's more than 20, it's going to break. Why didn't we catch this? Well, because we just didn't take enough time to slow down and evaluate every aspect of the design. We didn't make a full power budget for everything. We didn't do a full derating analysis. And we didn't do these things for one very good reason. Because those aren't the fun parts of making electronics. Those are parts of electrical engineering that are just work. Plain and simple. In retrospect, there are some things that we could have done to set ourselves up for success while minimizing the amount of work we needed to put in. If we would have just fed our entire push-pull control and gate drive circuit with a fixed voltage, that would have made verifying and designing such that less than 20 volts was always applied much easier. It would have been more difficult to make a mistake if we did that. I'd probably have chosen something around 12 to 15 volts, and designing the circuit with too wide of an input voltage range introduced the opportunity to make these types of mistakes. Now, will I ever make this design decision and set myself up to make this mistake again? No, probably not. I probably never will. Speaking of. Wow, did you look at the time? It seems like we just finished building the next UPS control board and got it installed in the computer chassis. Sweetness! Rock and roll. All that's left to do is power on and see if our design changes fix the problem. Alright, here we go. 3, 2, 1. What the? Wow. We really got a lot done here today. New transformer, done. New UPS board, done. Circuit mods, complete. We built our second UPS prototype. Now we're ready to dive into another round of testing. We implemented those circuit level fixes we were just talking about in the previous video, so hopefully we identified the true root causes for the circuit failures we observed in our first board. If this circuit fails again in the same way as the old one, we'll know that at least one of our root causes wasn't quite right. Regardless of if we were right or wrong, we're certainly about to find out, so tune in for our next videos because we'll be kicking off our UPS testing in just a couple of days. If this board doesn't explode, man, that would sure be great. If you want to see this UPS working, let me know by hitting the like button on this video, following us on Twitter, or leaving a comment letting us know what's on your mind. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for everyone, and thank you for staying till the end. Bye!